Hello students, in the series of lectures on thermal radiation, this is the first one, and in this lecture we are going to see some of the general information related to thermal radiation, some important radiation laws, and how can we use these laws to solve some practical problems. So point wise, we'll just see some of the general information that is required to be remembered related to radiation. See, the first point, it is the radiation differs from conduction and convection heat transfer mechanisms in the sense that it does not require the presence of a material medium to occur. We have already seen that in case of conduction or convection, some material medium is required. Like in conduction, mostly it is the solid, or it can be liquid or gases, but some material is required for conduction. In case of convection, it is some fluid, either liquid or gases, that is required to transfer energy from one place to another. But in case of radiation, from the source to the destination, if there is no material medium, even then the energy can be transferred. Okay. The second point is energy transfer by radiation occurs at the speed of light and suffers no attenuation in vacuum. Since the energy transfer mechanism in case of radiation is by electromagnetic wave propagation, and that is why it is taking place at the speed of light, and it suffers no attenuation in vacuum. If there is any vacuum, then it will suffer no attenuation. The complete energy will be transferred from the source to the destination. Now, third point, you see that radiation can occur between two bodies separated by a medium colder than both the bodies. So you can see that intermediate medium between the source and the destination, that intermediate medium even can be colder than both the source and destination, but still radiation can occur from source to destination. Next, you see it is a volumetric phenomenon in general, but remember, if we consider some opaque material like metals, in those cases generally radiation is treated as surface phenomena, because if it is opaque in nature, if the material is opaque in nature, so the radiation at the internal to that particular body emission is not going to come at the surface, because if the material is opaque, non-transparent. Okay, so that is why in those cases basically it is treated as surface phenomena, but in general you remember that radiation is a volumetric phenomena. Now, the nature of propagation of the energy in through radiation, according to Maxwell's theory, this energy transfer takes place via electromagnetic waves in radiation, and electromagnetic waves transport energy like other waves and travel at the speed of light, as you know. So according to Maxwell, it is the electromagnetic wave propagation by which the energy is transferred from one place to another place in radiation. And you know that electromagnetic waves are characterized by their frequency and the wavelength, and you know the relationship between the frequency and wavelength. You see that lambda is the wavelength and nu is the frequency, where the c is the velocity of light in the medium where it is transferring. Okay, so that velocity of light in that medium, you see, can be written as the velocity of light in vacuum divided by the refractive index of that medium. Okay, so if it is a vacuum, then c will be replaced by c naught. Okay, because in that case the refractive index will be 1. Now Note that the frequency of an electromagnetic wave depends only on the source and is independent of the medium. Okay, so it is very important that the frequency of electromagnetic wave depends only on the source and is independent of the medium. Okay, so this is one of the things that you have to remember. And the frequency of an electromagnetic wave can range from very small, like few cycles, to it can be millions of cycles per second. Okay, so the frequency of electromagnetic wave, depending upon the temperature of the body, it can vary from a very small value to a very high value. Okay, now according to Einstein postulation, the theory of electromagnetic radiation, that is the based on this theory, according to Einstein's theory, the electromagnetic radiation is propagation of collection of discrete packets of energy called photons. Okay, so in this view, each photon of frequency nu is considered having energy h into nu. So if nu is the frequency of the photons and h is the Planck's constant, then h into nu is the energy content of that particular photon. Okay, so you can see that you can write this frequency in terms of wavelength. So if you just put it, it will be Ch by lambda, and the value of the Planck's constant you can see in SI unit, it is 6.625 into 10 to the minus 34 joule second. So most important thing here, you please note this one, this is very important, that the relationship between the energy content and the wavelength or the frequency. You see, as the wavelengths are smaller, you see the energy content is very high, and if the wavelength is large, then the energy content is very small. That is why if you consider like X-ray, gamma ray, these are having the frequency is such that their wavelengths are very small. Since their wavelengths are very small, they having very high energy. That is why you know that X-ray and gamma rays can damage our tissues, our body. On the other hand, if the wavelengths are very large, like radio waves, microwaves, in those cases the energy contents are respectively less. Okay, and that is very clear because they are inversely proportional. So this is a very important point that you please note down here. Now here you see the whole spectrum of the electromagnetic radiation, and you see in the whole spectrum that it is basically the wavelength in microns is there in the x-axis, and you observe that very small wavelengths are basically of gamma rays. You can see the gamma rays are very small wavelengths, or cosmic rays are very small, whereas X-ray, you can see its range is 10 to the minus 4 to 10 to the minus 2 micron. This is, so they are falling under a very small wavelength, and their energy content is very, very high. Okay, that you remember. On the other hand, you see the microwaves having respectively larger wavelengths, more than 100 microns. As you can see, radio waves are also there. They are also having higher wavelengths. Here you can see that electrical power waves is basically the power supply that is taking place. It is around 50 hertz, right? So if you just convert it to wave, you'll find that these are also very, very large wavelengths in the order of 10 to the power 10 microns. Okay, very, very large. So these are the two extremes, very small and very large. Now you observe carefully this region, which is shown by red, which is the thermal radiation. So in the whole spectrum, the thermal radiation spectrum is 0.1 micron to 100 micron. Okay, so 0.1 micron to 100 micron is the thermal radiation. This part is we are basically interested here of the whole spectrum of electromagnetic radiation. Now you see that within that thermal radiation there is a small zone which is from 0.4 to 0.7 micron. 0.4 to 0.7 micron window that you can see here. Here this is the visible range. Okay, this is the visible range, and 0.4 corresponding to violet, 0.7 corresponding to red. And if the wavelength is more than 0.7, then it is infrared. Okay, and that we again infrared within the thermal radiation range up to 100. On the other hand, you see if it is below 0.4 micron, then it is ultraviolet. Okay, and ultraviolet range you can see up to 10 to the power -2 in the lower limit. Okay, so these are the certain things that you try to remember that will help you to understand the things better at the spectrum level. Now what we have seen there, that the thermal radiation emission is a direct result of vibrational and rotational motion of the molecules. Okay, so how the thermal radiation takes place, because if you consider this is a body, and you know that this body consisting of its different atoms there, atoms, electrons are also there, molecules are there. So these vibration and the rotations of these particles like atoms or molecules, okay, so because of that, because of their vibration, because of their rotational motion, basically electromagnetic waves are generated, or that is emitting out of that body. And you know that this vibration or rotation of the molecules and the atoms are actually measured in terms of temperature. The bulk nature of the motion of the atoms and the molecules is represented by the temperature, you know. If the temperature is more, that means basically the motion of the molecules or atom is larger. Okay, so temperature is a direct indication of the rotation and the vibration of the molecules and atom that it consisting of. So you can see this temperature is directly related to the emission, how much radiation is taking place. Okay, so the basic reason, the fundamental reason why any body, because of its own state, it emitting radiation, the reason is it is actually consisting of molecules and atoms, and since those molecules and atoms are continuously vibrating and they are having motion, rotational motion, because of that they are continuously emitting thermal radiation. Okay, so this is what is the basic reason behind the thermal radiation. Now what we call light is the visible portion of the electromagnetic spectrum, and which lies within the thermal radiation band you have seen between 0.4 micron to 0.7 micron, right? So within this range of wavelength, that is the visible spectrum from violet to red. So thermal radiation is a volumetric phenomena in general, we have already seen. However, for opaque solids such as metals, radiation is considered to be surface phenomena. And since the radiation emitted by the interior region never reach the surface, and that is why it is considered to be a surface phenomena. So note that the radiation characteristics of surface can changed completely by applying a thin layer of coating on them. So for this thing, like in case of metals and all these, if you give a very thin coating, okay, so that thin coating can completely, thin layer of coating can completely change the radiation characteristic, like its emission characteristic or the absorption characteristics can be completely changed if you give a thin coating on it, because already we have told that for opaque solids it is the surface that dictates the radiation characteristics. Now coming to the black body radiation. A black body is defined as a perfect emitter and absorber of radiation. Okay, so at a specified temperature and wavelength, no surface can emit more energy than a black body. Okay, so black body is basically a kind of idealized thing, reference where the definition is given such a way that at a particular temperature, let us consider a body having temperature T. So at that temperature, if it is a black body, then it will emit the maximum amount of thermal energy. Okay, so at a particular temperature, it will emit the maximum amount of thermal energy, or it will absorb the maximum amount of thermal energy at that temperature. That is what is called the black body. So black body having maximum capacity of emission and as well as maximum capacity of absorption. Okay, so this is what is the basic idea at a particular temperature. So if this body is not a black body, suppose its temperature is T, and of the same size and shape, if you consider another body having temperature T, so if you compare, if this is a black body and this is a non-black body, then definitely if you compare the emission, thermal radiation that is coming out of these two bodies, you will find that for the black body it is the maximum. Okay, if you compare with respect to non-black body at the same temperature. Similarly for the absorption also. So a black body is a diffuse emitter, which means that it emits radiation uniformly in all direction. Okay, so also a black body absorbs all incident radiation regardless of the wavelength and direction. So black body radiation characteristics are independent of the wavelength and independent of direction. This is what is the basic idea. That means regardless of the wavelength and direction, it emits, it absorbs everything. This is what is the idea. And from the point of view of emission, in all direction it will emit equally. Okay, so it is kind of independent of direction. There is no direction specific emission. It is not that in a particular direction it will emit more, in another direction it will emit less. In case of a black body, it is uniformly distributed over the direction. The concept of diffuse emitter will clear later on mathematically. We will see those things, but right now this is the basic idea. Now already we have seen the Stefan Boltzmann law that is related to the black body radiation. To be very specific, it is the radiation energy per unit time per unit area, basically the radiation flux. Remember what is the unit? Always remember the unit is watt per meter square. So the radiation rate of radiation energy per unit area. Okay, so that if it is a black body and if it is having temperature T, if T you express in Kelvin, then that is this T. Then by using this formula, EB is equal to sigma into T to the power 4, where sigma is the Stefan Boltzmann constant. Okay, and the value of this constant in SI unit, try to remember this result, 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. And remember, this is very important, the temperature must be expressed in absolute temperature scale. Okay, so if it is degree centigrade, you have to add 273 with that to convert it into Kelvin. And EB is called the black body emissive power. So emissive power is basically the radiation flux. Emissive power is basically the emissive flux. Okay, that means its unit is watt per meter square. That you have to remember. And since it is a black body, that is why black body emissive power. Now coming to another law related to the radiation that we have not covered earlier. This is Planck's law, or to be very specific, Planck's distribution law. So in the Planck distribution law actually tells about the spectral black body emissive power. Okay, so spectral black body emissive power means if you observe, let us consider this is a surface, and you see from this particular surface the thermal energy is coming out, right? The thermal energy is coming out. So when the thermal energy is coming out from this body, you see that it is not that a particular frequency or the particular wavelength that is coming out. It is basically the energy that is coming out that may have all this spectrum. That means from a very low value, from a low value of wavelength to a very high value of wavelength, everything is present. Okay, so when you try to define that how much energy is coming out, it is basically we mean that the total energy considering all these wavelength that is coming out. But if we want to define, let us consider this particular having wavelength, say lambda 1. So, or this one is suppose lambda 2, this one is say lambda 0. So there are different wavelengths, and these wavelengths, you know, for the thermal energy it is in the order of generally 0.1 micron to around 100 micron. For the thermal radiation, we know it varies from 0.1 micron to 100 micron, and it is almost continuous. It is not certain discrete values like that we have drawn here. It is continuous variation from 0.1 micron to 100 micron. So all these wavelengths are present, infinite wavelengths between 0.1 and 100 micron on meter, those are present, that is coming out. So the definition for a spectral emissive power is basically what is the emission energy per unit wavelength. This is what is the idea. So per unit wavelength, what is the energy that is coming out. So it is kind of an intensity, like per unit wavelength how much is coming out. Okay, so try to understand the unit. Unit is like the watt per meter square per micrometer. So per micrometer how much is coming out. So this is what is spectral black body emissive power. Okay, so if you this is what is the spectral indicates what? Spectral indicates per unit wavelength how much emissive flux is coming out. Okay, or emissive power that is coming out. So if you want to find out what is EB, EB means what is the emissive power, black body emissive power, that means what is the total energy, rate of energy that is coming out per unit area. So for that, what you have to do, you have to simply integrate this quantity EB lambda over d lambda. Okay, so and you have to integrate from the whole spectrum of lambda from 0 to from a very low value, maybe from 0 to infinity. Ideally it should be from 0 to infinity, but actually you know for the thermal radiation it is generally 0.1 micron to 100 micron, because in that range you will find maximum of the thermal radiation. Okay, so if you do this integration, E spectral emissive power and multiplied by d lambda, and if you integrate you will get the EB. Okay, so Planck's law actually given the expression of what should be the value of the spectral emissive power, and it is function of temperature. Definitely it is function of temperature, and its value you see it's C1 divided by lambda to the power 5 exponential C2 by lambda 2 minus 1. This is what is the expression, and where C1 C2 you can see from this expression, where C0, remember this C0 is basically the velocity of light. 0 actually indicates the velocity of light in vacuum, but if it is some other medium, then in place of C0 it will be C, the velocity in that medium. Okay, and you know that how they are related, velocity in that medium and C0 how they are related, that you know by the refractive index. C is equal to C0 by n. So this expression where C1 is 2 pi h is Planck constant into C0 square, where that means it is basically C1 has been defined for the vacuum. Okay, if it is not vacuum, some other medium is there, then C naught will be replaced by C. That you have to remember. Similarly, C2, it is also again written as HC0 by K. So if it is not vacuum, then it is to be replaced by C. And where K is the Boltzmann constant, and whose value is 1.3805 into 10 to the power minus 23. So if you just put all these values, that means if you put this expression of EB lambda in this expression, in this integration, and after that if you do the integration from 0 to infinity, and it can be shown that this EB will be finally converted into sigma into T to the power 4. That is what is the Stefan Boltzmann constant. So Stefan Boltzmann constant actually result of integration of the Planck's law. So from the Planck's law we get the spectral black body emissive power, the expression for the spectral black body emissive power, and then if you integrate over the d lambda from 0 to infinity, you will get the black body emissive power. That means over the all wavelength range from 0 to infinity, it will become sigma into T to the power 4. Now try to visualize this Planck's distribution law that we have seen here in the mathematical form. If we try to see in a graphical form, probably we'll be able to understand the expression better. So here in the y-axis, it is basically the spectral black body emissive power, that means EB lambda, which has been plotted, and here it is lambda wavelength, which is in the x-axis. Now you observe that there are different curves, each curve corresponding to a particular temperature. Let us consider this curve. This curve is corresponding to 10,000 Kelvin. This curve is corresponding to 3000 Kelvin. This curve is corresponding to 500 Kelvin, and like that. So if you fix the temperature, if you just fixed one particular temperature, say 3000 Kelvin, you observe that with the change of wavelengths, you see that in the x-axis it is basically plotted from 0.1 micron to 100 micron, and you observe that between 0.1 and 100 micron, most of the energy is falling in that. Only a few energy probably will be outside that region, only a very few. So that is why the thermal radiation is basically between 0.1 micron to 100 micron. Now you observe that at a particular temperature, let us say 3000 Kelvin, if you observe that how the spectral emissive power is changing with wavelength. As the wavelength is increasing, gradually the emissive power is increasing, then it reaches some peak and then again decreases. Okay, so this is the first observation, and that is happening for almost all the temperatures. The second observation you see, that is as the temperature is decreasing, its peak value as the temperature is decreasing, its peak value is decreasing, as you can see, and as the temperature is increasing, the peak value is increasing, which is quite obvious. Now, the third point, that if you observe carefully, that the peak value, if you just consider the peak value for each temperature, you see they are corresponding to definitely some wavelength, and you see as the temperature is decreasing, the wavelength is increasing. So you see that as the temperature decreasing, its peak value is occurring at a wavelength which is larger than the previous one. Here you see the peak value reaches at 1000 Kelvin at this wavelength, and which is larger than what is happening in case of 3000 Kelvin. So somehow it can be shown from this expression mathematically also, that this lambda and T are somehow inversely proportional, okay, corresponding to the peak value, corresponding to the peak power. Corresponding to peak power, you observe that this lambda and T are inversely proportional, okay, and this lambda T corresponding to the peak power, lambda T corresponding to the peak energy, is basically some constant, okay. So this is another important law of radiation, which is called the Wien's displacement law, okay. So that is again coming from the basic law of Planck's distribution law. So you observe carefully, the Planck's distribution law gives rise to Stefan Boltzmann law. Planck's distribution law gives rise to Wien's displacement law also. So here this is the expression for the Wien's displacement law, and it has been found that this product is a constant, and it has been calculated is approximately 2897.8 micrometer Kelvin, okay. And if you integrate that, we have just told earlier that if you integrate the spectral emissive power over the all wavelength range from 0 to infinity, what you are going to get is the Stefan Boltzmann law, which is sigma T to the power 4. But remember, this Planck displacement law is defined for a black body. That is important thing that you have to remember. So Planck's displacement law is true for black body, Stefan Boltzmann law true for black body, Wien's displacement law is true for black body. Now, to avoid numerical integration of Planck's equation, because if you want to find out how much energy is required for a particular range of wavelength, in that case definitely you have to do the integration, okay. Suppose you want to know this body, let us consider this is a body, suppose its temperature I am giving you, suppose the temperature is T1, and I want to know, tell me how much energy is coming between 0.4 micron and 0.76 micron. Suppose I want to know that between 0.4 micron and 0.76 micron, in this range, how much energy is going out. You know that this particular range is something specific. What is this? This is what is the visible light. So because of its temperature, the energy that is coming out, maybe a portion is visible light, maybe other portion is in the form of thermal radiation, maybe other portions may be infrared or ultraviolet, whatever that may be. But I am interested that how much of the energy which is coming out is falling within the visible range. So as a light, how much is coming out? We may be interested to know this kind of question. So for that, what you have to do? You have to integrate the Planck's distribution law, because Planck distribution law gives you the basic idea that at a per unit wavelength how much is coming out. So EB lambda. Then what you have to do? You have to multiply d lambda, and you have to integrate from 0.4 to 0.76 micron. So in this range, if you do the integration, you will find out that how much energy is coming out within that range from 0.4 to 0.76. So in this range, how much energy, black body energy, is coming out per unit area, that you can find out from this integration. But this integration is not very simple, as you have seen the expression of the Planck's distribution law. So to avoid this integration, what we can do, we can define some fraction called f lambda, and you see that this fraction is defined as basically this integration which is in the numerator divided by the total black body radiation from 0 to infinity. Okay, so in the numerator it is from 0 to lambda. See, from 0 to lambda, which is there in the numerator. You see, let us consider this is the variation in the black body radiation. So from 0 to lambda, maybe this is lambda, say this is lambda. So from 0 to lambda, if you do the integration, you will get this much of energy. And we are actually, so this much of energy is the numerator from 0 to lambda. From 0 to lambda, if you integrate. And in the denominator, it is basically the total area. In the denominator, it is basically the total area from 0 to infinite. From 0 to infinite, the total area. That is what is EB, the black body emissive power. That is in the denominator. Okay, so this fraction is what is called f lambda. But if our problem is this one, we are interested to find out how much is 0.4 micron to 0.76 micron, then what we do? 0.4 micron to 0.76 micron, if you want to find out, so what you have to do then, you first find out what is the energy up to 0.76, and then you subtract what is up to 0.4, and then you will get this energy window, right? So what you do, you find out f lambda 0.76. f 0.76 means it is basically 0 to 0.76, right? Then you find out from the table what is f 0.4 micron. That means it will give you from 0 to 0.4, and if you subtract these two, that will give you f 0.4 to 0.6 in that range, 0.4 to 0.76 in that range. Okay, so this is what is the technique. So from the table you find out this one, from the table you find out this value, and then you subtract, you will get this value. So once you get this fraction, if you want to find out what is the energy, you simply multiply it by sigma t to the power 4, you will get that energy, or that integration you can simply find out. Okay, so this is what is the technique. So let us, here you can see the table, how the table actually looks like corresponding to lambda t. This table is actually given for the f lambda value. Let us take one problem and try to solve it. So this is what is the idea that we have explained just now. Take a practical problem and try to understand how we can make use of Planck's distribution law. But actually we are not going to directly use the Planck's distribution law, in a sense that we are not going to integrate, we are going to use the fraction. Okay. So the question is, the temperature of a filament of a light bulb is 2500 Kelvin. Okay. And assuming the filament to be a black body, because it is very important, otherwise we will not be able to apply the Planck's law. Determine the fraction of radiant energy emitted by that filament falls in the visible range. That means between 0.4 and 0.76. How much? Okay. So also determine the wavelength at which the emission of radiation from the filament peaks. So this is simple. So what you do, you have to find out that radiant energy which is coming out between that range. So for that, what you do, from the table, you see this is what is the table, and in this table you need lambda t, then you can find out f lambda. So corresponding to f 0.76, if you want to find out what you required lambda into T. Temperature already given, that is 2500 Kelvin, and lambda what you put is 0.76. Remember, the unit is micrometer into Kelvin. So put this is micrometer, this is Kelvin. So simply multiply these two, you will get some value of lambda T. So use that lambda T, whatever that value is, use that lambda T and find out what is the corresponding F value. Suppose that F value is this one. So that F value you just write here, that is f.76. Exactly in a similar way, find what is f.4. So in that case, you use the value of lambda as 0.4 multiplied by the temperature, that is 2500, and corresponding to that you find out what is the value that is coming out. Maybe for this one, maybe this is the value, let us consider. So after that, what you do, you just take the difference of these two, that means f.76 minus f.4, that will give you some value which is nothing but the fraction which is in between. So this range now you will get. Okay, so this is like 0.4. Okay, this lambda 2 is like 0.76. Just think in that way. Okay, so you get then this value, because this fraction actually, always remember, is defined from 0 to that value. Okay, so from 0 to that value, then minus 0 to that value. So you will get this fraction. So once you get this fraction, if you have to find out what is the energy that is coming out, so f lambda 1 lambda 2 is basically this difference that you have already calculated multiplied with that sigma T to the power 4. T is 2500 Kelvin. Sigma, you know, that is the Stefan Boltzmann constant. So if you multiply, then you will get what is the radiation energy that is falling within the visible range. Okay, and for the peak value, it will be clear from the diagram that for which wavelength it will give you the peak value. So for that, what you do, mathematically you can do in that way. You can use Wien's displacement law. You know that corresponding to the peak value, already you know, corresponding to the peak value, this lambda T is a constant. Okay, so what was its value? That is 2897.8, which is a constant corresponding to a peak value. So you just write 2897 something, and T you know is 2500. So what is the lambda corresponding to the peak, that you can easily find out. 2897 divided by 2500 will give you the result. Okay, I think the problem is clear to you. Okay, in the next class we'll see some of the radiation properties. Thank you.